Welcome to the video for skill number 77. I can solve rational equations and inequalities. Alright, solving rational equations and inequalities. We'll start our notes on page 77A. A rational equation is an equation that contains one or more rational expressions. In the example I've provided below, I've got this rational expression and I've got this rational expression, and because they are set equal to each other, we have what is called a rational equation. Now, most people will tackle this problem very quickly using that dreaded form of cross multiplication, and you can do that. However, I'm going to teach you a method which is consistent for all rational equations, or at least all that I can think of. So please try to approach it this way because it'll be more versatile. In the first step, what we need to do is find the least common denominator. So it's very easy with this expression. Our least common denominator is n minus 3 times n minus 4. If you have an equation where there is maybe something in the denominator that needs to be factored, there would be a prior step. Step 0 would be to factor. So if you want to add that to your list, step 0 is factor, and then step 1 is to find the LCD. Step 2, multiply numerators and denominators by missing pieces of the LCD. Now this is a lot like what we would do if we were adding rational expressions, and that's why I would encourage using this method, because it reinforces adding rational expressions. Step 3 is nice because all we're doing is we are canceling the denominators by multiplying all terms by the denominator. And if we multiply all pieces by n minus 4 times n minus 3, then what happens is it cancels out in the numerator and in the denominator. So we do that to both sides, and it cancels out. So what we wind up having is we just set the numerators equal to each other. And from there, it's a rather clear, simple algebraic problem. We first distribute in the 6 to get 6n minus 24. We distribute in the 5 to get 5n minus 15. And we solve for n. The last thing we want to do is check our answer against the constraints. Our constraints were n cannot be 3 and n cannot be 4. So there is no conflictions there. So we are happy with the answer of n equals 9. We'll see in the next example a problem that conflicts with the constraints. And also the next example is a good example of why we avoid the cross-multiplying method. Alright, so example 2. What we have here is we have our first rational expression and we add a second rational expression, and that is all equal to a third rational expression. And as you can see in this example, we can't cross-multiply because we have two terms over on the left-hand side of the expression. So our method is first we factor and then we find the LCD. And the LCD in this case is 2 times x minus 3. In step 2, we multiply each fraction by the missing piece of the LCD. So in our first fraction, we are missing the 2. So we multiply top and bottom by 2. In the second fraction, we are missing the x minus 3. So we multiply top and bottom by x minus 3. And in the third fraction, we're missing the 2. So we multiply top and bottom by 2. In step 3, we cancel out all of our denominators by multiplying the whole equation by our LCD. It's a nice trick that allows us to cancel out the denominator all the way across and make it a very easy, straightforward algebraic problem. So from there, 4x times 2 is 8x. X times x minus 3 is x squared minus 3x, and 12 times 2 is 24. this expression, we combine our like terms. Negative 3x and 8x is 5x. And we realize that what we have is a quadratic expression. That quadratic expression we can use the quadratic formula on, or hopefully it's an easy expression to factor. And in this case it was a factorable expression, and we wind up getting zeros at negative 8 or at 3. And here's where step 5 comes into play. We check our answers against the domain. So our domain was constrained. We said x cannot be 3. So we cancel out that as an answer. Because x can't be 3, we don't allow that, and the only answer available is x equals negative 8. Notice that this relied on our ability to do factoring and or quadratic formula. There it comes back again, the importance of factoring to this chapter. The quadratic formula, for those who don't recall it, is negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we did that for this formula, we would get negative 5 plus or minus the square root of 25, which is b squared, minus 4 times 1 times negative 24, all over 2a. Simplifying this further, we get this to be negative 5 plus the square root of 121 over 2, which is negative 5 plus or minus 11 over 2. This gives us the answers negative 8 and 3. So this is perhaps a longer way. Factoring it would definitely be a better course of action, but sometimes we just can't manage to factor a problem. So this works great for fractional answers. Alright, moving on to the next part of the skill, rational inequalities. And solving a rational inequality, so real briefly, a rational inequality is an inequality that contains one or more rational expressions. So you might have 2 over x minus 3 is less than 5. So in that, here's your rational expression, and this makes it an inequality. Less than, greater than, maybe less than or equal to, etc. And to solve a rational inequality, you have to consider two cases. The first case you consider is that your least common denominator is positive. So we would consider x minus 3 to be a positive number. And then your second case, you assume it to be negative. And it is important that we look at both cases. If we only look at one case, we're not finding a complete solution. So let's see how this plays out on the next page. If at this time you wish to take a break on notes, I'm going to split my lesson into 2 days. The first lesson will occur up until this point, and the second lesson will be what is covered in the rest of the video. Starting our notes on page 77C, for example 3, we have the rather straightforward inequality 5 divided by x plus 3 is less than or equal to 5. So in this case, our LCD is positive. Sorry, our LCD is x plus 3. So we're going to look at two conditions. One where the least common denominator is positive, i.e. x plus 3 is greater than 0, and one where the LCD is negative. If x plus 3 is greater than 0, then we are saying in this case x is greater than negative 3. And we'll call this case 1. Case number 1. And over here, x is less than negative 3 is case number 2. From there, we go about solving it. So what we can do is we multiply each fraction by the missing pieces of the denominator, so of the least common denominator. So this fraction was missing x plus 3 in the top and bottom, and we multiply by x plus 3. Because we're assuming x plus 3 is positive, nothing happens to the inequality. However, on the other case, we're assuming it's negative. So when we multiply both the top and bottom by the denominator, the inequality flips. This flipping of the inequality applies really in step 3. So when we're canceling out the denominators, we get 5 is less than 5 times x plus 3 versus 5 is greater than. And as you can see, they still look very similarly in the two cases. The only difference is the sign is, or the direction of the inequality is turned. In step 4, we go about solving it. So I'm going to scroll up and move in because this is where the real significant difference happens. Okay, so in the end, we have 5 is less than 5 times x plus 3. We simplify that down, and we wind up getting negative 2 is less than or equal to x. If you wanted to, you could think of that as x is greater than or equal to negative 2. And what I've done is I've graphed that aspect, x is greater than or equal to negative 2. And then we considered the case to be that the denominator was positive, and in that we said x was greater than negative 3. That's to be found up here. The positive case, x is greater than negative 3. So we graph that as well on a number line. X is greater than negative 3. And then what we're looking for is the spot where both conditions are true. Both x is greater than negative 3 and x is greater than or equal to negative 2. And that only occurs on this half of the graph. So in condition 1, or case 1, these two constraints are true only when x is greater than negative 2. In case 2, we do the same process. We solve it down. In this case, we wind up getting x is less than or equal to negative 2. So we graph that on a number line. And then our case was assuming that the denominator was negative. So we graph the x is less than negative 3. And we want to grab the condition where both of those are true. And that's only true when x is less than negative 3. So our final answer is these two answers combined. So what we have is the time when x is greater than negative 2 or the time when x is less than 3. If we wanted to think of this graphically, and that's why we learned graphing first, we could imagine what the graph of this looks like. And there's it looks like there's a vertical asymptote at negative 3, a horizontal asymptote at 0, and then the graph of this looks something to the effect of a curve that does that, and a curve that does that. And then we're trying to find when is it less than 5. So 5 might occur something like this. So the spots where it's below the line of 5 is right here, and all of this. So here x is greater than negative 2, and here x is less than negative 3. The area that is not below the line of 5 is from negative 3 to 2. Negative 3 to negative 2. Thinking about it graphically is not necessary, but sometimes it is quite useful to look at it this way. Sometimes people will graph it on their graphing calculator and use that as a guide to help inform them. Here's a second example. In this case, we assume the LCD to be positive in here and the LCD to be negative. We go about the process of solving the equations, making sure in the negative case our inequality is flipped, and in the end we arrive at the condition where either x is less than -2 or x is greater than -2. We add in our case where the denominator was positive, and we see that if we were to graph these two lines, there's no spot where both of those are true. So we get no solution if the denominator is positive, whereas in case number 2, we get a spot here where it is true, where both conditions are true. So that's where we get the solution. Alright, so the key ideas and concepts in this video are solving rational equations, which might be 2 over x plus 1 minus 5x over x minus 4 equals 7. And the second part of the lesson is solving a rational inequality, which would be 5 over 3x minus 4 is less than or equal to 18. I have not tried solving either one of these. I don't know if the answers are clean, so I wouldn't bother trying to solve them unless you want a little challenge. The skill test for this will very likely consist of 2 or 3 problems where you're solving a rational equation and 1 or 2 problems where you're solving a rational inequality. It's important that we be able to factor and find the LCD of rational equations or rational expressions if we want to be successful on this skill. Thank you.